Hey, I'm Dmitry Mukhtasimov and I'm learning machine learning. And I'm using Feynman technique to improve my learning process. But I don't like explaining to myself because it's not much fun, so I'm recording this video. And in the last video, I recorded my understanding about the gradient descent method. Actually, I showed it on a derivative, and I would call it like derivative descent, an invented term of mine. But the video is not much explanatory. I guess, it's kind of clumsy. So I decided to improve it and record another one. I created a Jupyter notebook which shows all the steps of descending to the function minimum, local minimum. So welcome to the screencast. Here's Jupyter notebook I crafted to show gradient descent in action. It doesn't have a nice animation, but it's actually have a printout for a step-by-step process of finding function local minimum. So let's go over this notebook and I'll just describe every cell, and then I'm going to describe the gradient descent algorithm. Alright, so the first cell is just import, and it also tells you that you need to install some dependencies. Well, the notebook is stored without results, meaning that all these images that you see here on the screencast, you are not going to have them in the Git repository because I striped them out. So if you want to see those screenshots, those images on your screen, on your own screen, you'll have to run this notebook yourself. So and to do so, you need to install matplotlib and PrettyTable. You can also do it by using Poetry. All right, so next cell is actually defining the function we want to find the local minimum for, and its derivative. So the function is as you see here, x squared minus 6 times x plus 10, and its derivative is 2 times x minus 6. And here we have a cell just to draw the graph of the function. Alright, the next cell is actually the most interesting one. It's the implementation of derivative descent, the invented term that I have. And so let's take a closer look at it. So it's provided with a function and its derivative. It also provided with initial value of a. A is a point at which we start finding a local minimum, and finally it will point to the local minimum of the function. Learning rate, default value is 0.1, but we are going to use a different learning rate value, 0.3. So just, to get to the local minimum faster. Max error, it's interesting thing. So basically, when you program an algorithm, you can't just be exactly precise like you do in math. So you have to accept certain error that is good enough for you. So for this case, I set it by default to 0.0001. And actually, if you make it small enough, you can actually get to the real function local minimum, which is at the point x equal 3. And this actually happens just because of the precision of float operations in computers is limited, and so at some point it just flips into the closest closest number it can represent, and it appears to be free. But in our example here, I'm just keeping this relatively big error, and you will see that we are not reaching to the actual function local minimum. Max iteration, well, we have to set it just not to get to infinitive loop, because in case the function, the derivative doesn't converge to 0, well, we might get to infinitive loop and never end this algorithm. That's why I set max iteration to 20. And Xlearning is a kind of technical thing. It's expected that you provide a list, a Python list, into this argument, so you can collect the learning steps that the algorithm is getting. And if you don't provide it, a new list will be created for you. So the most interesting part is here, the algorithm itself. So as you saw in the previous video, we are taking steps iteratively until we reach the local minimum of the function. And so this is implemented here. As you see, this for loop, it's for making the iterations. The next line is just keeping those steps for us to be able to print them later. So here we are actually printing them. You can see here in the table. Well, the next one is actually the implementation of the algorithm. So we are calculating a derivative at that certain point, and then we compare the derivative absolute value to the max error that we can tolerate. So basically, if we are close enough to the local minimum of the function, we just break, we just finish, and we return the value of the point that we have. But in case we are far from the local minimum, we are doing actually the iteration step. So we are calculating the next value of a. So here in the comment I wrote a mathematical expression that like the next value of a, which I represent like a sub I plus 1, equals current value of a, which I represent like a sub I, minus learning rate times the value of the derivative at current point of the algorithm, so at current value of a. And here's the implementation in Python. So we already calculated the value of derivative at point A, and so we multiply it by learning rate and subtract from a, so we are getting the next value of a, and then we go to the next iteration until we reach the good enough error, and then once we reach it, we break and return the value of a. The next cell is just actually we are calling that function, so providing it with the function we want to find local minimum for, its derivative, starting value of a, and learning rate that we want, so it's 0.3 here, and we provide a list that we want to collect learning steps. Alright, so here are some helper function. We are printing this table, and let's go to the results, which are more interesting, and so we can review every iteration of the loop. Okay, so firstly we see that the result is printed. As you see here, it's not exactly free, but the error, so 3 minus this value, is less than the error we wanted. So that's good enough for us. And so let's see how it worked on iteration. So the iteration number 0, a equals 0, a equals 0, and so let's look at the graph as well. So on the graph, I represented a function here. The trail a values that we took, and the error in red, the red bar is representing error. So the first iteration, a equals 0, we calculated derivative at that point, and it was minus 6, and error was 6 because it's absolute value of derivative. And as you can see, because the value of derivative is negative, then a, and we subtract from a, so this means that the value of a will be increased. And so you see here the next point of a that is being tried is 1.8, which is greater than 0, right? And what is notable here is that the derivative is not only showing the direction to which we should change the value of a, it also tells us how fast should we change it. So we will see it on the next steps. So on iteration number 1, we actually again calculate the derivative at that point, and so the error turns out to be even less, right? So we are approaching to the local minimum of the function. So we are taking the next iteration, and so as you can see, the next value of a is 2.52, which is like the difference between the previous iteration value of a and the one before it is much less, right? So if you see, like, we advanced it at the first step, we advanced a to 1.8 units, and then we advanced it to 1.72, right? So it's less than the previous one. So the rate at which we change the value of a is also changing, so it's becoming less with each step. And if we can check the derivative here again. Its absolute value is more than the error that we want, so we go to the next step. In the next step, you see the value of a is 2.808. So now we advance it a like for about 0.3 units. So, and you can also see this on a graph. So firstly we advance it a like here, this distance, then it was less, and then even less, and here actually multiple points sits here. The closer we get to the function local minimum, the more points, the closer the points sit together, and the scale of the graph doesn't let us show all the points, so they're getting crowded here, and just drawn one on another. All right, so next we move again, we increase A gradually, and so you see here, like we advance A so little, like between iteration number 4 and 5, we advance A like on 0.04 units, and then it's like the next one is 0.02 units, and then it's even less and less and less. And so basically this the use of derivative for finding the function local minimum is really great in two ways. So first, it shows the direction to which we need to change the value of the point to approach to the local minimum. And second, because the derivative the closer is the derivative to the local minimum of the function, the smaller derivative is, and this is also affects how fast we approach to the local minimum. And what why it's useful, it's because we do not jump over the local minimum in that case. So basically we are just approaching to the local minimum from the left, and we're never jumping over, because the derivative value is decreasing as well. I mean, the absolute value of the derivative is decreasing as well. But actually, even if we jump it over, it's not a big deal, because the algorithm is going to correct it, and the value of the derivative is going to be positive in that case, and then it will make the A variable actually decrease towards the local minimum of the function. And I can show it on the next graph actually. So so here we choose a starting point of A variable on the right of the local minimum of the function. And so as you see, it's also approaching to the local minimum as well, but from the other side. And you can see here again, the first steps are bigger, and on the graph as well, you can see they are big and getting smaller and smaller as soon as we approach to the functional local minimum. All right, so that's it about the notebook. You can find it with the link below. Thank you for watching. You can find the link to the Jupyter Notebook in the description below the video. I will post also a link to the root of the Git repository that I used to produce that Jupyter Notebook, and probably I will add more stuff to that repository, so you can subscribe to it as well. And yeah, welcome to the comments with your questions and critics. Thank you. Bye.